All right, hello everyone. So we have the following problem. It's a calculus 2 problem. Using the Lagrange error bound, find a bound on the approximation of ln of 1.05 with a fourth degree polynomial. All right. So first of all, let's look at what the Lagrange error bound says. So you're given f of x with n plus 1 derivative centered at a. So what we mean by the center, just as a reminder, if you're figuring out a Taylor polynomial, if you recall, you took a bunch of derivatives at a certain point. The center is that point itself here. All right, well, what the theorem says, the error bound theorem says is this. If you find the error between the function value at a specific point minus the polynomial nth degree Taylor polynomial approximation, that's what that PN stands for. Let me just highlight that right there. Then the error, which is that, is no more than this quantity right here. So that's what we mean by the word bound. It's basically that the error cannot get larger than that quantity there. So x, a, n, and m all stand for something. N in that formula is basically the degree of your polynomial. A is where you're centered at, and x is the value that you're actually trying to that you're plugging into your function to approximate the value that you're looking for. And m is a value which is equal to the maximum value of the nth plus 1 derivative between a and x. Now, I know that's a lot. I think it'll make more sense in a minute once we actually start writing things down and actually start doing this. So the first thing you're going to need is you're going to need a function to work with. Now, I was trying to approximate ln of 1.05 here, so I'm going to work with f of x equals ln of 1 plus x. And there's a known series for that. And I would be centering it at 0. And in particular, because there's a series that's centered at 0 for ln of 1 plus x that we know, and then we can take derivatives of. That's why. And a couple things that we're going to need. We're going to need our x here, which is the 0.05, because if you plug in 0.05 in for x, you get 1.05 in the inside, and the ln of 1.05 is what we're trying to approximate. And n equals 4 here because it's the fourth degree Taylor polynomial. So essentially we'd be plugging things into that formula that you see up there. And the only thing we're missing is what m is. Now, to find m, you need to find at least 5 derivatives. Why? Because m is the maximum value of the nth plus 1 derivative. So n is 4, then n plus 1 is 5. So I'm going to take my function, take some derivatives of it, as you can see. And the fifth derivative comes out to be 24 over 1 plus x to the fifth. And what I'm looking for is a maximum value of 24 over 1 plus t to the fifth, absolute value of that between 0 and 0.05. And really what we call the variable isn't really that important. But here x is technically, we're looking at it as in this case, as a number, so that's why we kind of switched to t here. Anyways, so the absolute value is just going to be the same thing as not having the absolute value, because your function itself is positive in that interval from 0 to 0.5 inclusive. So what's the maximum value of this function? Well, if you look at the function itself, you can tell that the maximum value is going to happen at 0. Because, maximum value between 0 and 0.5, it's going to happen at 0, because if you plug any number larger than 0, as the values of t get larger as you go away from 0, as you go towards 0.05, the denominator is going to get larger, and therefore the overall fraction gets smaller. And your function, if you were to draw that, it looks something like this, essentially. That's what it would look like. And so your max value happens when t equals 0, or 24 over 1 plus 0 to the fifth is 24. Now, for those of you that say, you know what, I want something more strict here, a little more rigorous, what you could always do is this. You could also just work with this function and take its derivative, and you would see that if you took the derivative, it would be decreasing. and therefore you would have a maximum value at 0. So that's another way to tell. Okay, and we found our m, and we found everything that we needed. So if we go to the formula again, f of x minus Pn of x less than or equal to m, x minus a to the n plus 1 over n plus 1 factorial. And if we were to plug everything in, f of 0.05 minus p4 of 0.05 less than to equal to m is 24, x was 0.05, a was 0, so 0.05 minus 0 is just 0.05, n was 4, so 4 plus 1, 5 over 5 factorial. And furthermore, f of 0.05 is like saying ln of 1.05, plugging in 0.05 into that function. And now here's a thing, 5 factorial is like saying 5 times 4 times 3 times 2 times 1, that's 120. So 24 goes into 120 5 times. So this whole expression is now equal to 0.05 to the 5th power divided by 5. I don't need the absolute value itself because the number itself is already positive. So we'll go ahead and just compute that, see what it looks like numerically here. So 0.05 to the 5th divided by 5, and you can see it's 0.00000 1, 2, 3, 4, 5, 6, 7. Looks like 7 zeros and a 625. Seven, 6, 2, 5. So I hope I counted the correctly. And yeah, so basically this would mean that the error between the actual function value and the approximation from the polynomial is going to be less than or equal to 0.70625. It does not mean, however, a lot of people confuse the fact that a lot of think that what we're saying is the actual error is 7 zeros and a 625. That's not it. It's just saying that that's the largest error that you can possibly have. You might have something that's smaller than that as the error. That's perfectly possible, but nothing will be larger than that. Okay. All right. Well, I hope this helps. Thank you for your time.